Written by James Carter, author of Quantum Physics for Beginners, available at Barnes & Noble. Imagine a giant circuit with a battery, a switch, a light bulb, and two wires each 300,000 kilometers long. The distance light travels in 1 second. These wires would stretch halfway to the moon and back, connecting to a light bulb just 1 meter away. The question is, after closing the switch, how long would it take for the bulb to light up? Is it half a second, 1 second, 2 seconds, 1 seconds, or none of the above? You'll need to make some simplifying assumptions for this circuit. The wires must have no resistance, and the light bulb must turn on immediately when current passes through it. Before I reveal the answer, commit to one in the comments. This question ties into how electrical energy gets from a power plant to your home. Unlike a battery, electricity in the grid is alternating current, AC, meaning the electrons in the power lines just wiggle back and forth. They never actually travel anywhere. So, if the charges don't come from the power plant to your home, how does the electrical energy reach you? When I used to teach this subject, I would say that power lines are like flexible plastic tubing, with electrons inside acting like a chain. A power station pushes and pulls the electrons back and forth 60 times a second. At your house, when you plug in a device like a toaster, it allows electrons to run through it. As they encounter resistance in the toaster element, they dissipate their energy as heat, toasting your bread. It's an easy visualization, but it's wrong. For one thing, there's no continuous conducting wire running all the way from a power station to your house. There are breaks in the line, like in transformers, where one coil of wire is wrapped on one side and a different coil on the other. Plus, if electrons carry energy from the power station to your device, why don't they carry energy back to the station when they flow in the opposite direction? The truth is, it's not the electrons themselves that carry the energy. In the 1860s and 70s, Scottish physicist James Clerk Maxwell made a breakthrough, realizing that light is made of oscillating electric and magnetic fields. His equations, known as Maxwell's equations, govern the behavior of these fields. In 1883, Maxwell's student, John Henry Poynting, explored how energy flows from one place to another, leading to the Poynting vector, a simple formula that describes the energy flux through an area per second. This formula applies not only to light, but to any situation where electric and magnetic fields coincide. Consider a simple circuit with a battery and a light bulb. The battery's electric field extends through the circuit at the speed of light, pushing electrons around. These create electric and magnetic fields outside the wires, and according to Poynting's theory, energy flows from the battery to the bulb through the space around the wires. So, what's the answer to our giant circuit question? After closing the switch, the bulb will light up almost instantaneously, in roughly 1 seconds. The correct answer is D. The electric and magnetic fields propagate through space to the light bulb, which is only 1 meter away, in just a few nanoseconds. This understanding of how electrical energy flows changes the way you think about everyday devices like light switches. Next time you flick one on, remember it's the electromagnetic waves around the power lines delivering your power. For more insights like this, check out Quantum Physics for Beginners by James Carter, available at Barnes & Noble. Thanks for reading.